Okay, good afternoon. Welcome to, what is this, Math for Kids number 17?
17.
17. We're going to do more continued fractions today. So yesterday, let's just review a little, real quick. Yesterday we wrote down the continued fraction that looked like this. I'll write it here.
I'm just showing the Fibonacci
1
numbers.
1 over 1 plus 1 over 1 plus 1 over 1 plus, oops, 1 plus 1 over, and it went down. And we found these things called the convergents that were equal to 1, 2, let's see.
I think it was 1, 1.
1 over 1, 2 over 1, 3 over 2, 5 thirds, and then 8 fifths, etc. And these are called the convergents, and we found those by evaluating pieces of the continued fraction. First we evaluated just the 1 here, then 1 plus 1 over 1, then 1 plus 1 over 1 plus 1 over 1, and then we got these numbers.
The Fibonacci numbers.
Yeah, and it turned out to be the Fibonacci numbers, and that's really neat actually,
Yeah.
that that's the case. But we want to figure out a way, or I'm going to show you a way. The problem is that what I'm going to show you, can you grab the eraser for me real quick? What I'm going to show you is, it's a little bit too complicated to prove it to you. But I'm just going to show you a neat way to do this. So we have to
fractions that go on forever?
Yeah, you can. Well, yeah, actually, yeah. This will help you. This will show you how to evaluate continued fractions that go on forever. So first, we have to understand some special numbers. The special numbers in continued fractions that we're looking at are these numbers here. So the 1 plus 1 over. All of the continued fractions we're going to look at are always going to be 1 over something. Okay, so we're just going to look at these numbers that go down here. So we might look at a fraction like this, 2 plus 1 over 3 plus 1 over 7 plus 1 over 2, something like that. And all we'd be concerned about is the 2, the 3, the 7, and the 2. Okay?
Yep.
And then we're going to try to find, is there a neat way to find the convergence for this? And it turns out there is. And it's a really neat process. So what we're going to do is we're going to write down those numbers that we encounter in the continued fraction, and then if there's more, we'll go over there. And we're going to write them down here in a little box. Let's see how much more room I need. I need about this much room. Okay. So let's look at the continued fraction 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. Okay? So what we do is, all we do is write down 2, 3, 4, 5. 2, 3, 4, 5. In our one that produced the Fibonacci, all we'd write down is 1, 1, 1, 1. Right?
Yep.
Okay. And then over here, we just write 1 and 0 and 0 and 1. Okay? So we start out like this. This is our continued fraction generating machine.
I wonder why we have to write the 0, 1, and 1,
okay?
0.
And then to get the convergence, all we do is we multiply down and add. So 2 times 1 is 2, plus 0 we get a 2. 2 times 0 is 0, plus 1 is 1. Okay? Now we keep doing the same process. 3 times 2 is 6, plus 1 is 7. 3 times 1 is 3, plus 0 is 3. Next we go 4. 4 times 7 is what?
4 times 7 is 28.
28. And then plus, 28 plus 2. 4 times 7 is 28, plus 2 is?
30.
30. 4 times 3 is?
That's 12.
Plus 1 is?
13.
13. 5 times 30. Ooh, that's a tricky one.
Oh.
5 times 30 is?
5 times 30 is 150.
Okay, plus 7 is?
157.
And then 5 times 13, do you know what that is?
I know it's 65.
65 plus 3 is?
68.
68, okay. And then, so these are our convergents, 2 over 1, 7 over 3, 30 over 13, and 157 over 68. So that's the last one. So if we evaluate this continued fraction, we should get 157 over 68. Okay? Now, this would take a long time to evaluate, but you want to do it real quick just to check?
Yeah.
Okay,
It's going to take a long time.
Well, I'll fill it in. 4 plus 1/5 is 21 fifths. 21 fifths. And what is 1 over 21 over 5?
It's 5/21.
Okay, so 5 over 21. This is going to be 63 plus 5, which is 68 over 21. And what's 68 over 21?
21/68.
21/68. Now 68 times 2 is what?
Is 136.
136 plus 21?
Is 157.
157. This is equal to 157 over 68. So we got it.
Yay!
So now, do you see how much easier our new little continued fraction machine is?
Yeah.
Okay, so let's do it for a simpler one. Now, actually, let's do it for our one. It's 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 going down, so that all of our numbers up here are just ones. Okay, and it could go on forever. We can make it go as far as we want. And then we'll calculate what these convergents are. Okay, you ready?
Yep.
Okay. Now we should see the Fibonacci numbers. 1 times 1 is?
1.
Plus 0 is?
1.
1 times 0 is?
0.
Plus 1 is?
1.
Okay. 1 times 1 is?
1.
Plus 1 is?
2.
1 times 1 is?
1.
Plus 0 is?
1 times 1 is 1 plus 0 is 1.
1. 1 times 2 is 2, plus 1 is 3.
Yep.
1 times 1 is 1, plus 1 is 2.
Yep.
1 times 3 plus 2 is 5. 1 times 2 plus 1 is 3. 1 times 5 plus 3 is 8.
We got 2 sets of Fibonacci numbers.
1 times 3 plus 2 is 5. 1 times 8 plus 5 is 13. 1 times 5 plus 3 is 8. So,
we got 2 sets of the Fibonaccis.
we got the Fibonacci number. So the convergence for this are 1 over 1, 2 over 1, 3 over 2, 5 over 3, 8 over 5, and 13 over 8.
So we should get 13 eighths.
Yeah. So, well, let's see. How many ones are over here? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. If I evaluated this fraction, I'd get 13 eighths. Okay, but I don't want to do that. I want to show you some other really neat stuff. Okay?
Yeah.
Watch what happens with our little convergence, with our fractions here. 1 over 1 and 2 over 1. Okay? They always have a very special relationship to each other. When I multiply it this way and I subtract multiplying that way, so I take 1 times 1 minus 1 times 2. 1 times 1 is?
1.
Minus 1 times 2 is minus 2, so this is minus 1. What if I do this way? 2 times 2?
4.
4 minus 1 times 3.
Minus 3, which is 1.
1. How about 3 times 3?
Is 9.
Minus 2 times 5?
Is minus 1.
Which is minus 1. So I went from minus 1 to 1 to minus 1. 5 times 5 is?
5 times 5 is 25.
Minus 3 times 8, which is?
24. 1.
So I get minus 1, 1, minus 1, 1. 8 times 8 is?
64.
Minus 5 times 8. 5 times 13?
Is 65.
65 minus 1. So when I do these funny cross multiplyings, I always get a plus 1 or a minus 1.
Cool.
Yeah, it is pretty cool, isn't it?
Some really neat things about continued
Yeah,
fractions.
continued fractions are really amazing.
Too bad they don't teach them in school
Too
anymore.
bad they don't teach them in school anymore, but luckily we have this great video to learn about them.
And we have this great whiteboard.
And we have this great whiteboard that we made. Okay, so one last example. And then we'll see if that pattern holds true for any continued fraction, or was it just something special about the Fibonacci numbers. Okay, so you tell me. I'm going to have a continued fraction. What do you want the first number to be?
But 2.
2 plus 1 over
3.
plus 1 over
4.
plus 1 over
9.
9 plus 1 over
1 over 7.
7. Okay, great. So we're going to write down 2, 3, 4, 9, 7. Now, before I taught you the continued fraction machine trick, this would have taken a long time to figure out, right?
Yeah.
Now let's just figure it out. 2 times 1 is?
2.
Plus 0 is?
2.
2 times 0 is?
0.
Plus 1 is?
1.
3 times 2 is?
6.
Plus 1 is?
7.
3 times 1 is?
3.
Plus 0 is?
3.
4 times 7 is?
Is 28.
Plus 2 is?
30.
4 times 3 is?
That's 12.
Plus 1 is?
13.
9 times 30. Ooh. 9 times 30 is?
Well, I know that 10 times 30 is 300, so that's 270.
270 plus 7 is?
277.
277. 9 times 13.
Whoa. 10 times 13 is 130 minus 13. 130 minus... So 130 minus... That's what we have to do.
Yep, 130 minus 13 is?
117. No.
Okay, 117.
Yeah. 117.
Plus 3? 117 plus 3 is?
120.
120. Okay. Now we have to do 7 times 277. Okay, so 277 times 7. I hope this is on camera. So that's going to be 1400. What's 7 times 70?
490.
490
And
plus
49.
49. So that's 1000 plus 800 plus 130 plus 9, which is 1939.
Whoa!
Plus 30.
So
What's 1939 plus 30?
it's 1969.
1969. And then 7 times 120. That's a little easier to do. 7 times 120 is?
7 times 120, so 7 times 100 is 700. 20 times 7 is 140.
So that's 840
Yep.
plus 13.
Which is 853.
853. Okay, so there's our continued fraction. Now let's see if our little cross multiplying works. So this continued fraction that I just erased, unfortunately, is equal to 1969 divided by 853.
Here's our cross multiply.
Okay, 2 times 3 is?
6.
Minus 1 times 7 is?
7.
So we get minus 1.
1.
7 times 13?
So 7 times 7 is 70, and 7 times 3 is 2191.
91. Minus 3 times 30 is?
Is 90.
Minus 90. I get a 1. Huh.
Looks like we get it.
Wow, now we got a really complicated one. And maybe we'll do this later. 30 times 120. But we think that 30 times 120 minus 13 times 277 should equal minus 1. And we think that 120 times, that 277 times 853 minus 120 times 1969, that should equal 1.
Whoa!
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 Whoa, but we don't know. So this is why continued fractions are so neat. They have all these incredible properties, and you know what? It's just numbers. So you just play around with some numbers and you find these amazing properties.
Yeah.
Yeah, isn't that neat?
It's so awesome.
It is. It's fun. All right. Good job today, sweetie. Like this. And tomorrow, well, I don't know. We'll figure out the next thing on continued fractions. Good job today, honey.